This video is about the combined gas law, which is really helpful when you don't want to change just one variable, you want to change multiple variables. So we've talked about these laws on this side. We have Charles' law, Boyle's law, and Avogadro's law. Now individually, each one only allows us to change one condition, but we can use this information and put them together to make one law that has all the variables combined in it. And let's look at the relationship between each one of these variables. Okay, so I'm going to look at this one here. Pressure and volume are going to be multiplied by each other, but I can see that when volume is on top, temperature is going to be on the bottom. So I'm going to put those together. If pressure and volume are going to be multiplied by each other and volume is on top, temperature has to be on the bottom. And I'm going to give myself, that's my initial conditions. I'm just going to make a mirror image here for my final conditions. Okay. But now I have to figure out where moles comes into play. I can see if volume is going to be on top, moles is going to be on the bottom. So here, volume is on top, so moles is going to be on the bottom. So here I just cleaned that up a little bit. What I really like about the combined gas law is, yes, I can use it for a problem where I want to change, the pressure and the volume or something like that, and I want to figure out how temperature changes. I can use it like that. But what I also like about it is I don't really like to memorize Boyle's law, Charles' law, Avogadro's law. I don't like to memorize each one of those individual laws. What I did is I just memorized one equation here, the combined gas law. And why it's so useful to me is because when I'm doing a problem, if I'm reading the problem and just the pressure and the volume are changing, what I do is I write the combined gas law and then I circle pressure and volume. And the things that are on the bottom weren't mentioned, so they're going to be constant. They cancel out. And so what I get is P1 V1 equals P2 V2. So that is Boyle's law, but I just used the combined gas law to find it. Now let's say again, say I'm reading a problem and the problem mentions moles changing and pressure changing, but volume and temperature were not mentioned in the problems. I can just go to the combined gas law and I circle my moles and my pressure and I cancel out everything else. And what I get is P1 over N1 equals P2 over N2. So the combined gas law can get you any of the individual gas laws and some others that didn't get names. So now let's do the combined gas law to practice our calculations here. Again, I'm going to read through the problem and I'm going to circle the variables and write down what kind of characteristics are they, volumes, temperatures, things like that. Okay. A sample of carbon dioxide gas has a volume of this liter, so that's my volume 1, and a pressure of this, so that's my pressure 1, and a temperature of 33 degrees C. That's my temperature 1. Remember, we need to convert that to Kelvin, so we're going to do that before we start the problem. What will the temperature be? So I'm trying to find T2. If the pressure is increased to 1275 torr, so that's a pressure, that must be my P2, and the volume is also increased to 20 liters, so that is my V2. Okay, here I just kind of cleaned things up. It was getting a little bit messy. So what I did is I took the information out of the problem and I made myself a little table here of pressures and volumes and temperatures, like this. I wrote down my initial conditions. I did convert my temperature from Celsius to Kelvin. It is accurate to the ones place, so this is also accurate to the ones place. And for my final set of conditions, I wrote down my second volume, my second pressure, and I'm trying to find my second temperature. All right, so what I'm going to do now is I'm going to go to the combined gas law, and I'm going to write it down here, and I'm just going to see what I have, what I need. Okay, so I need a volume, so I need my volumes because those are changing. I need pressures because those are changing. I need temperatures because those are changing. But in the problem, it doesn't mention anything about moles. I don't need that to be a part of my equation. So I'm going to rewrite this like this. All right, I'm going to keep on working on the algebra here because I want to find T2, and it's on the bottom on this side. I want to manipulate this equation so that T2 is on the top and everything else is on the other side. So the first thing that I'm going to do is I'm going to multiply both sides by T2, so those will cancel out, and I'll get T2 P1 V1 over T1 equals P2 times V2. All right, then I'm going to multiply both sides by T1 so that those cancel out. I get T2 like this. And I'm trying to get that T2 by itself on both sides. So the last thing that I'm going to do is divide both sides by P1 V1. Okay, so those would cancel out. And what I get, I'm going to rewrite this right here. What I get is that T2 equals P2 times V2 times T1 divided by P1 and divided by V1. So I've got everything on the other side. Now I just have to put the numbers in. All right, so now what I'm going to do is I'm going to take the numbers from this side and put them into my equation. P2 is 1275 torr. V2 is 20 liters. T1, 306.15. I'm going to make sure I mark my sig figs there. P1 is 735. And V1 was 15.2 liters. I'm going to make sure that I go through and I make sure my units cancel, liters and liters. Okay, I'll get Kelvin out of this. That's the thing that doesn't cancel out, and I'm trying to find a temperature, so that makes sense. On my calculator, I got 698.78 Kelvin. And for sig figs, let's see, this had 4 sig figs, 3, 3, 3, and 3. So I'm going to mark this to 3 sig figs. I'd have to round that up. So this would be 699 Kelvin. All right. Okay, let's try another problem. I'm going to go through and mark the variables here. Okay, I have a temperature. I need to make sure that I put that in Kelvin. An internal pressure of 1 atmosphere. That's a pressure. It's thrown into a fire until the new temperature reaches this. So that is my new temperature, and I need to make sure I put that in Kelvin. What is the new pressure? So I'm trying to find P2. All right, so if I do the same thing I did in this problem, or I did in the last problem, and I kind of keep track of my variables. That was degree C. If I put my temperature in to Kelvin, I'm adding 273.15. So that's 298. This is to the ones place, so I'm going to mark that to the ones place. Okay, so for my final conditions, I'm trying to find P2, and my temperature 2 is 2010 degrees Celsius. So again, I'm going to add 273.15 to that. And this was accurate to the tens place, so this is going to be accurate to the tens place. All right, the next thing that I'm going to do is that I'm going to take those variables and I'm going to look at my combined gas law, and I'm going to circle the ones that I need, and I'm going to cancel out the ones that I don't. The problem mentions pressure and it mentions temperature, so I'm going to circle pressure and temperature for each side. It doesn't mention volume or moles, so I don't need those. Because the problem doesn't mention it, it means they're being held constant. And the next thing that I'm going to do is just rewrite that with the ones that I need. Okay, so I need to put in my pressures and my temperatures there. I'm trying to find pressure 2, so I'm going to rearrange this equation so that pressure 2 is by itself on both sides. So I'm going to multiply both sides by T2, and I would get T2 P1 for T1, and then those cancel out, equals pressure 2. Okay, so now I'm going to put my temperatures and pressures in. So I'm going to use this information and I'm going to put them in this equation. So temperature 2 was 2283.15 Kelvin. Pressure 1 was 1 atmosphere. Temperature 1 was 298.15 to the ones place. And that will give me P2. All right, on my calculator, I got 7.657, and my units are, let's see, that's Kelvin, it's atmospheres. 4 sig figs. This had 3, this had 3, and this had 3. So this is going to have 3, and I should get 7.66 ATMs. Now, I do like to always think about the problems after I finish them, like, does my answer make sense? And what I saw here is that the temperature increased drastically from 25 to 2,000 degrees. And I'm looking for what's going to happen to the pressure there. So if the temperature increases, it makes sense to me that the pressure would also increase. That's technically called Gay-Lussac's law, and it's not one that we specifically talked about, but it's one that we can use the combined gas law for. But they are directly proportional. So as the temperature increases, the pressure is also going to increase. So it makes sense to me that my pressure went from 1 atmosphere all the way to 7 atmospheres. The last thing in this video that I want to talk about is when we're doing a changing conditions problem, just like the ones we've been doing, but we're going to be changing to a special set of conditions called STP. STP stands for standard temperature and pressure, and that's a very specific set of conditions. It is 0 degrees Celsius, or 273.15 K, and 1 atmosphere. So anytime somebody says we're changing the conditions to STP, we know that we're going for 1 atmosphere and 273.15 Kelvin. Let's practice with this problem down here at the bottom. It says that we have a volume of gas. So we have a volume 1, and it's collected at 25 degrees C. That's a temperature one, but we're going to convert that to Kelvin. And 645 millimeters of mercury. That's a pressure one. What will the volume be at STP? So anytime you see those words, you know that you are trying to find the volume at standard temperature, which is 273.15 Kelvin. So that's going to be your T2. And your pressure is going to be 1 atmosphere. That's going to be your P2. What I did here is I just, again, cleaned it up. I put my variables in a little table here. I gave myself an initial set of conditions, and then I put my final set of conditions over here. This represents standard temperature and pressure. I'm looking for the new volume. We need to make sure that our units are the same on both sides. So if I put in volume in liters, I'm going to get out volume in liters. The temperatures always have to be in Kelvin, and I have that here. The pressures, one side is in millimeters of mercury and the other side is in atmosphere. And that's a problem because the units aren't going to cancel out, but it doesn't matter which one we choose. We can either put both of them in atmospheres or both of them in millimeters of mercury. It doesn't really matter. I'm going to choose to put my pressure 2 into millimeters of mercury because that's an easy conversion for me. I know how to convert 1 atmosphere to millimeters of mercury. It's 760 millimeters of mercury. That's just an easier calculation than going from kind of a weird 645 to atmospheres. That would have taken me a little bit longer. Now, like I always do, I'm going to start with the combined gas law. P1V1 over T1N1 equals P2V2 over T2N2. And I'm going to circle the variables that are changing, and I'm going to cancel out the things that stayed stable. So I need a volume, I need a temperature, and I needed pressure. So I'm going to circle those on each side. Moles did not change, so it's not going to matter in my equation. And I'm just going to rewrite this with just the ones I need. I'm going to rewrite that down at the bottom of my screen. And I'm going to rearrange the equation so that volume 2 is by itself. So that's what I'm looking for, is volume 2, so I want it by itself. What I need to do is I need to multiply both sides by T2. When I do that, I get T2 P1V1 over T1 equals P2 V2. And now I need to get rid of the P2 on each side. So I'm going to divide by P2 here, divide by P2 there. Those cancel out. And what I'm left with is T2 P1 V1, T1 P2. Lots of variables. Okay, so that's going to be my equation. Now all I have to do is put these variables, those numbers, in there. All right, I need a little bit more room, so I clean things up a little bit. Now I'm just going to put those numbers in. All right, T2 was 273.15 Kelvin. P1 was 645 millimeters of mercury. V1 was 28.8 liters. T1 was 298.15. And P2 is 760 millimeters of mercury. When I did this on my calculator, I got 22.39, and with sig figs, let's see, this was, to 5, that had 3. This one had, let's see, it was to the ones place. I should have been more careful there. So that also had 3, and this had 3. So I need it to be 3, so I'm going to round that up. And so I got 22.4 liters. This number that we just calculated, that's a number that you're going to see come up in one of our other videos when we're talking about the ideal gas law, and also when we do some stoichiometry with gases. It's a special number. That is the volume that any mole of gas will occupy at STP. So it's a number that we can calculate. It's a number that you're going to see again, and when we see it again, we'll talk a little bit more about its meaning. So that was our video on the combined gas law. I just want to remind you that we started off with talking about how we got the combined gas law, and then we also talked about how you can use the combined gas law for any changing conditions problem. So instead of using just Charles' law, Boyle's law, or Avogadro's law, things like that, we can use the combined gas law for any of those changing conditions problems. And how we do that is we just keep the variables that we need, and we cancel out any variables that are not mentioned in the problem. Then we also talked about how we can use the combined gas law to do a changing conditions problem where we change the conditions to STP, which is standard temperature and pressure. If you're looking for some practice problems with the combined gas law, of course you can use it for any of the Charles or Boyle's law problems, anything like that. But you can also use it to do in your course pack, page 45, which is gas laws 1. It would be problem number 6. And on page 47, which is gas laws number 2, it would be number 3.